Hello guys, today we're covering section 5.2, the definite integral. So section 5.1, we went over, having a graph of a function, and we wanted to find the area under the curve of that function from like a to b. And like so far that has like a very geometric, kind of argument to it. We're finding areas of rectangles where the rectangles are sampling or, kind of based around a function. And we add up those areas to try to find this whole area under the curve. So far that is pretty nice. And we also understand that when we take more rectangles, as we try to get better and better approximation, when we take more rectangles, we end up getting better and better approximations. And we had things such as like upper and lower sums. We had, you can choose any other points we typically want, but typically what we're going to do is the left or right endpoints when we try to do these. But I'll kind of clarify when we go on. So the definite integral is basically a way to concrete what we're talking about and, create it, write it in a more solid manner, Like how can we take those ideas, generalize them a bit while still keeping that, this definition right there. Kind of like how we went from tangents to derivatives, now we're going to go from areas under curves to, integrals. So, the first thing we need to do is define the definite integral. Like, what is it? So the first thing is we need a function f. It's going to be defined on, AB. It's going to be defined for x between AB. Nope, we didn't say continuity. This doesn't need to be continuous, but continuity does play an important role in this kind of situation. So we can divide the interval into divide the interval AB into n subintervals of equal width of delta x is equal to b minus a divided by n. And we let x0 equal a, x1 equal to a plus delta x, xn equal b. And, those are going to be like our endpoints of the subintervals. And we're going to let, x1 star, x2 star, xn star, xi star, all the points that we're going to get and, be sample points in the subintervals. So again, all that means is that they're x1 should be between, x0 and x1. Well, x1 star should be between x0 and x1. x2 star should be between x1 and x2. This is kind of, we basically just if we stick to a subinterval, we need to approximate it. We can choose the height of the function at xi star. So then the definite integral of f from a to b is going to be the limit as n goes to infinity of the sum from I equals 1 to n of f of xi star delta x. So this is, let me just write it down. This is the sum of n rectangles with a height, where f of xi star will be the height, and delta x is going to be your width. And this basically is the idea of what I was saying earlier. We take better and better approximations, and we take more and more rectangles, then we get better and better approximations. So we actually expect that the limit should actually be the area, the area under the curve. So that n stands for the number of rectangles. And, note that this xi star, this xi, just remember what that xi star means, or what that I means. It just means, it's a placeholder. It means we sum from all the numbers going from 1 to n. So this is going to go to f of xi x1 star, then it would be plus f of x2 star all the way up to n. And if you guys you're not really sure, just look up sigma notation. You could just Google it for a moment. It's not too difficult to understand. It's just a bit of notation to make things look easier. So, we have that the definite integral, which is going to be the integral of a to b of f of x dx, that's how we say it, is an equal to the limit of those sums. We meet specifically we're going to call this a Riemann sum. That's what I'm going to be trying to call it from now on, which, we're going to touch on that in just a second. But, we're going to say the limit of Riemann sums. The limit of approximating rectangles. So the overall limit is what we're going to call the definite integral. So note we have this curly s right there. We have we have a and b there, so that's the place we were doing the area over. And we have the function, and we have that dx there. And we should note that we call that the definite integral of f from a to b if the limit exists and gives us the same value for all sample points. So what that tells us is that, it shouldn't matter where we're choosing to sample the function from, is that we should get the same numbers. And if, we should get the same limit. And if we don't, then it's not integrable. It's not nice. And if you just want a quick example of an example why this doesn't work, we could take a function f of x, which is equal to, we say 0 on the rationals. So this is let's say p and q are just integers. And then, if 0, we say it's 0 if x is equal to p over q for some, integers, and 1 if x is not equal to p over q. So for an example, this would be 1/2, f of 1/2, f of 3/4, f of 600, f of 2 billion over 307. Those will all be 0 because they're all rational numbers. And 1, the case when we can't represent them as a ratio of integers, and it's called irrational. So square root of 2 pi e, any of those numbers would give you 1. So the thing is, though, it's we could, at any interval we have, we could choose a sample point to be 0, or we could choose our sample point to be choose our sample point to be a number of this form, or we could choose a number of this form. And that's true for all intervals. So we could always choose, our function to have, to be 0, or we could choose a function to always be 1. And, the limit of just things being 0 is 0, the limit of things being 1 is 1, so that's why we have to have the same value. And this is where continuity kind of comes into play too. So, but again, if it does exist, if we satisfy those conditions, the limit exists, and it's true, and it's the same value for all sample points, then we say that f is integrable on AB. And each part of the definite integral has a specific name. So remember that, we're not integrating, but we're finding the area from A to B. So we need to make sure we indicate that. And we also need to indicate what we're doing. So this right here, that, that's going to be the integral sign. A is going to be the lower limit. B is going to be the upper limit. And then we have, the thing we want to integrate is actually going to be, inside of it, we say f of x. And that's going to be referred to as the integrand. And dx is basically what kind of determines the variable you're integrating from. So if you didn't have the dx there, I couldn't give you an answer. Yes, you're saying dx, but if you ever go into higher calculus, you'll have double integrals, and you'll have functions of 2 variables. And we need to specify which we're integrating with respect to 1 variable. So if I say the integral from f of x y dy, then I specify I'm integrating with respect to y. If I don't tell you which variable, if I don't have the dx there or dy, then I can't really tell you which one I'm integrating for. So the dx is important too, so make sure to not forget that. And the thing is, again, it's defined to be a limit of sums. And specifically, we call the sum part, the actual sum, we call them Riemann sums, like I just kind of mentioned before. And so whenever I try to talk about the definite integral, I'll say it's a limit of Riemann sums. Mostly because it's just better than saying, approximating rectangles, and, it's just nicer that way. And again, kind of what I just said, is that with that one function that was 0 on the rationals and 1 on the irrationals, that function is not integrable, and and it's kind of the case that not a lot of functions are integrable. But if f is continuous on AB, it only has a finite number of jump discontinuities, so it's only it only has a few problems, then f is integrable on AB. So just to kind of clarify what this might look like, let's just take this would be 1, 2, 3. Say we have the step function, so it goes 1, goes. So let's just say we have the step function. It's going to go from 0 to 1, open circle, 1 to say this is 2, 3, open circle, and then this. So, those have jump discontinuities there. There's a finite number of them. And what we have is that, these are just rectangles. This is actually just a square. It has, length 1 and height 1. This right here is like a rectangle. This will have like, height 2 and length 1. So that in itself is just very easy to calculate. That has a finite, definite integral. We could, calculate that really easy. So, there's some cases where, discontinuities are fine, but we need to have a finite number of them. If you have an infinite number of them, then that's where we get the case of like, the function I gave you. Which is actually, if you want to know the name of it, it's called the indicator function for irrationals. But for convenience, we usually just use the right endpoints to calculate the sums. Because, again, we want the limits to be the same for all sample points. So there's no reason for us to make them complicated. Like, the Riemann sum specifically is defined for arbitrary sample points. It just means, you're choosing some random point in there. So it covers left and right endpoints, it includes the center points of the interval, includes all the other points. You could choose. So, but again, for convenience, we choose the right endpoint because the definition of a definite integral says, that it doesn't matter what we choose. And this is kind of where the theorem comes in. This theorem is. So if f is integrable on AB, so if it's like, definite integral exists, then we say, the limit is like, well, the integral from a to b of f of x dx. So we say like, the integral of a to, the integral of f of x. And then we say like, then we specify we're integrating from dx. And then is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. And again, basically all this is saying, approximating rectangles, we're doing Riemann sums. We're just doing, rectangles where the heights are going to be f of xi, where the xi are the right endpoints. So our delta x will equal to b minus a divided by n, and our xi will equal to a plus I delta x. And again, that's just, how you define Riemann sums. Well, and for right endpoints, I would go from 1 to n. If it was like the left endpoints, so if it was left, oops, I spelled left wrong, then it would go from 0 to n minus 1. Because if we look at the interval, let's just say we stop at the right point, this would be like, x0, let's just say it's 0. x1, this was our first rectangle right here. And then our last one would be like, say this is xn minus 1, and this would be xn. This would actually be b. So our left endpoint would be this one right here. It would be xn minus 1. So, the right or left endpoints kind of correspond to like a shift, like either, we go to 0 to n minus 1 or I is equal to 1 to n. But really, we're going to do the right endpoints, so this is the case. So, the fact is, but that itself is not too important. I wouldn't worry about it too much. Just be a bit careful, just double check real quick if you're unsure. But, so definite integrals are defined in terms of sums. So in order for us to understand the definite integrals, then we need to understand the sums. So, it's kind of have a good idea of how, you want to use some useful formulas and properties of summations for these sums. And we have some very nice ones. So like the first one's going to be the sum from I equals 1 to n, of like n times n plus 1 divided by 2. So basically this is just saying, if you add all the numbers from 1 to 2 plus 3 plus all the way up to you stop at some number n, then that'll be equal to n times n plus 1 divided by 2. And the second one will be the same thing, but instead of just having those numbers, you'd have them squared. And the last one would be, the same one, but them cubed. So if they're squared, then you get n times n plus 1 times 2n plus 1 divided by 6. If it's I cubed, then you get just n times n plus 1 divided by 2 squared. Well, n times n plus 1 divided by 2 and the whole quantity squared. So again, this one was like, the sum of just the first n integers. This one right here would be of the form, 1 squared plus 2 squared plus 3 squared plus, n squared. And this I, represents where we begin. N is where we stop. So remember that I is just basically like a placeholder. It's how we would write the general form. Well, because like if you would want to write, let's just say you have like, cosine of like 1 plus cosine of 2 plus all the way up to like cosine of 1000. What we want to do is like, we could write it like this and it'd be annoying to write it like that always. So instead we could just say, okay, this starts at 1, goes to 2, and keeps on going up to 1000. So we can say, okay, well, let's just start at 1, goes to 1000, and we need some way to indicate what's happening to each of the terms. So if you look at each of the terms, we have cosine, and inside cosine is the thing that changes. So it's going to go from like 1, 2, 3, 4, all the way up to 1000. So instead of just writing, the thing that changes each one, we're just going to put that I. And that's how we'd write that sum. So, keep that in mind whenever you do I cubed as well. Sorry, but on a side note, it's kind of like important to understand this notation, understand the sums too. So, just kind of keep that in mind what those mean, but, that in itself is not too tricky. If anything, just kind of know when you see them. So the second one, if you sum a number like c times, so if you do like, if I give you like x plus x n times, and I have n x's, so that's just n times x. Or really n times, so if I do, do a number c, then it's just c is equal to n times c, where, c is a constant. And, that in itself, is easy. That's just a nice property. It basically says, you sum the same number n times and you just get n times that number. This one right here is basically saying, here you have, and this is kind of where, AI is the more general notation that we use for sums. So if we didn't have the AI there, it would look like, well, let's just say, I'm just going to write out, the first thing of the sum. Just be c times a1 plus c times a2 plus c times a3 plus all the way up to c times an. And if you look at all these terms right here, every one of them are going to have the same form, and all of them are going to have the c in it. So we pull out the c from them. We get c times a1 plus a2 plus a3 all the way up to an. And remember, the way I write this does not mean that, a2 and a3 are there. It's just a way to represent, we're going all the way up to an. So if an was 2, then we would stop, then it would just be this. If an was equal to 1, then it would just be this. It's basically just like an algorithm, or a recursive algorithm. We just keep on plugging in until our terminating thing, and our terminating thing will be our n. And then likewise, we have like ai plus bi inside the sum, the sum from I equals 1 to n of ai plus bi. That's equal to the sum of, of I equals 1 to ai to the n, to n. Well, the sum from I equals 1 to n of ai plus the sum from I equals 1 to n of bi. And the same thing with subtraction. And that idea is basically just like, let's just say if I'm giving you money, and each time I'm giving you money, I'm going to give you like, I'm going to give you like $1 and a penny. And I'm going to do that 10 times. So in the end, you're going to get $10.10. But that's the same thing as if I were to just give you like $1, if I were to give you the dollars all together, if I gave you $1, then I gave you $1 and I did that 10 times, and then I gave you the pennies. So that's what this means. It doesn't really matter how you add things up. Addition is kind of commutative. So if you're ever doing any finite sum like that, if you're only doing like a finite number of things, then you could just break it up. So let's do an example real quick. F of x is equal to x squared minus 2x. And that's going to be between 0 and 3. So this is like our AB. And we want to evaluate the Riemann sum with n equals 3. So we're going to have, 3 rectangles. And we want to evaluate the definite integral. So remember, the definite integral is a limit of Riemann sums. So with n is equal to 3, the width is going to be delta x is equal to 3 minus 0 divided by 3, because it was b minus a divided by n, which is equal to, as we said right here, 3 minus 0. We said n is equal to 3, the number of rectangles, so that's just 1. So we have 3 rectangles with width 1, and we're going to use the right endpoints. So remember that whenever we define delta x, we get those xi's. We get those endpoints. So remember, we would cut up into some intervals. It would be 0 to 1, 1 to 2, and then 2 to 3. And the way we get these numbers would be this process right here. Xi is equal to a plus I delta x, but a is going to equal to 0. And then we have just I times delta x. So x1 would just be, 1 plus 1 times delta x. x2 would be 2 times delta x, and x3 would be 3 times delta x. But our delta x, we said, was equal to 1, so we just get 1, 2, and 3. So those are going to be our right endpoints. So, remember that, so our, the right endpoints, the sum of the rectangles, the sum of the area of the rectangles with the right endpoints of, 3 rectangles is just going to be, the sum from I equals 1 to 3 of f of xi delta x. Remember that this is the height, and this is our width. So it would just be f of 1 times delta x plus f of 2 delta x plus f of 3 delta x. Where f of 1 is going to be, and again, those xi's are as sample points. So those are where we're going to be choosing to be the height. So we plug them into the function. So this is like, 1 squared minus 2 times 1. F of 2 would be, 2 squared minus 2 times 2. And then we have like, 3 squared minus 3 times 2. So that was going to give us like, negative 1, 0, and 3 respectively. And we multiply them by their widths as well. And then what we get is going to be that, 2. Because negative 1 times 1 is just negative 1, plus 0 times 1 is 0, plus negative 1, so negative 1, plus 3 times 1 is going to be 3, plus negative 1, so 2. So this is going to be our approximation. That's the Riemann sum for r is equal to 3, using the right endpoints. So far, that's an approximation. We don't know necessarily how good it is yet, but we can figure it out, because we can actually figure out what this limit is. So let's just say we need to evaluate the definite integral, the integral from 0 to 3 of f of x dx. So we need to find, the Riemann sum from I equals 1 to n of f of xi delta x, but we're going to do the arbitrary, we're still going to do the right endpoints, because, because it doesn't matter, we're just going to choose the right endpoints to make it easy. So what we're going to do with n subintervals, or n rectangles, because again, it's a limit of the number of rectangles, so we need to start off in a very general setting. We want to try to write this sum as like some expression that depends on n that's easy for us to work with. So that's what we're going to be doing. So if we have n subintervals, like n rectangles, then we're going to have like, delta x is going to equal to 3 minus 0, so that was a b minus a, divided by n. That's just going to be 3 divided by n. And then the right endpoints are going to be, again, defined as we had before, xi plus I delta x. But we said, again, that a was equal to 0. Our delta x is equal to like 3 divided by n. So it's going to be of the form 0 plus I times 3 divided by n. So our xi's, the sample points, are going to be 3i divided by n. And this is okay, because n is fixed, and I is going to go from I equals 1 to n. And that's going to give us all the right endpoints. So our sum, the Riemann sum that we want to take the limit of, is going to go from, like, again, the sum from I equals 1 to n of f of xi delta x. And that's going to be, and remember that our xi's now are equal to 3i divided by n, and our delta x is equal to 3 divided by n. So we plug everything into those functions. Well, you plug everything into the, the actual, like, sum. So, xi is equal to this. Our delta x is equal to 3 divided by n. And then we're going to plug everything in. So this right here is, f of 3i divided by n, which I plugged in right here, and this is what you get. So, 3i divided by n squared plus 2 times 3i divided by n. And note that I, is not an imaginary number. We don't care about imaginary numbers at all. It's just a number squared. So, now we've plugged in for f of like 3i divided by n, and this is what we get. This, again, that's just f of 3i divided by n times our delta x. So this is still at the height of the rectangle, and then we're going to just simplify. And we're going to do some algebra. So we get, 9i squared divided by n squared minus 6i divided by n. All I did was just simplify of these. And then what I'm going to do now is just going to go ahead and distribute the 3 divided by n to get that 27i squared divided by n cubed, because it's going to be 27, well, it'll be 9 times 3 is 27, and then we get, 3 divided by n times 6i divided by n, and we get that 18i divided by n squared. I remember one of the rules with the sums we had was that they also break up over sums and differences. So I wrote them like this. I went ahead and broke up the sum over the difference. And now, this is kind of the thing. So, the sum right here is like a function. In the argument of that function is going to be, this expression right here. And the only thing that depends on it is I. So the I we cannot remove. The I has to stay inside. If we try to move the I out here, then we basically just erase the whole meaning of the sum. But, n right here, our n, even though there's an n right here, the n is basically just telling us how long we go for. And that number is fixed. It does not matter. It only basically says, it doesn't actually tell you about, it doesn't really determine what's inside. It doesn't really determine the behavior of the sum. And because of that, it's kind of being treated as a constant, and so is this 27, so we could treat them, so we can pull them out. So basically, the only thing that matters is we can pull out the 27 over n cubed, and likewise, we could do that with the 18 divided by n squared. So we still have to leave the I squared and the I inside the sums. So this is what we get in the next step. 27 divided by n cubed times the sum from I equals 1 to n of I squared. And then, minus 18 divided by n squared times the sum from I equals 1 to n of I. But, what are these again? So let's go up real quick. Okay, so let me just kind of clarify. So this one is the sum from I equals 1 of n squared to n of I squared, and the other one's just I. But we have these right here. Here's the one for I squared, here's the one for I. N times n plus 1 divided by 2n plus 1 divided by 6 for I squared. And then, the other one's going to be n times n plus 1 divided by 2. So we can plug those in. So we're going to plug those in, we plug in those the formulas that we have for those sums, and then we're just going to simplify. And this is what you get. 9n times n plus 1 times 2n plus 1 divided by 2n cubed minus 9n times n plus 1 divided by n squared. And note that, you could simplify right here, but we don't really care about simplifying. It doesn't really matter. Or you can just leave it as is. So lastly, this is where we're going to get to the definite integral. So the definite integral is going to, again, be the integral from 0 to 3 of x squared minus 2x plus times dx, because 0, 3, because we're doing it over x squared minus 2x, that's going to be our integrand. And again, it's the limit of Riemann sums. We've chosen, what we found was, an arbitrary Riemann sum. So arbitrary n. So we didn't choose any specific n, so this formula works for all numbers. It works for all, n's. It works for all, rectangles. So if you wanted a billion rectangles, we could plug it into that formula. If you wanted a quintillion rectangles, we wanted 3 rectangles. It doesn't matter how many rectangles we want, or how many subintervals we want. That formula will work. So it works when we plug in the limit as n goes to infinity. So we said, this is the Riemann sum. We figured out an expression for it, so we just plugged it in. And then what we did here is just, foiled out the expression and just did some algebra. So we get, 18n cubed plus 27n squared plus 9n divided by 2n cubed. And, the same expression over here. Well, the same kind of thing over here. But now we're going to take the limit as n goes to infinity. This kind of behaves like a horizontal asymptote. This is like a polynomial with respect to n. But really it's like, here you have 18n cubed divided by 2n cubed. So the n cubed would cancel, leaving you with just 9. And then, And then here you'll have, 27n squared divided by 2n cubed. So that'd be just 1 over n. And then, over here you would just have 9n divided by 2n cubed. And then those would you basically still get 2 over 9 over 2 times 1 over n squared. The fact is the highest degree here is going to be n cubed. The highest degree here is also n cubed. So the only thing, so the limit as n goes to infinity is just going to be the ratio between them. Likewise right here, I think this should be n squared. Or I think I made a typo there. Should be just n squared. Yep. So that way the limit right here is going to be, the ratio of like, just the leading, the things of the coefficients of the, ones with leading powers. You have like n squared and n squared, so it's going to be 9 divided by 1. This over here was just going to be 18 divided by 2. So it's just 9 minus 9. So 9 minus 9, that's just 0. And if you're a bit unsure why this is true, you can also just try to verify it on your own. You should be able to have the tools to evaluate the limit without me needing to explain it. So we got the definite integral. We got the actual limit to be 0, which is actually, I don't know, I think it's cool. And, all right, so we still have a few more things to do. All right, so, sorry, I just gotta double check the time. I mean, it's still right there, but I just have to double check something. So, we still want to do some more examples. Let's evaluate the following integral by interpreting it in terms of area. So let's do the integral, the definite integral of, of the absolute value of x minus 5 from 0 to 10 dx. So the integral, is going to have like the integrand of x minus 5. So let's just, if fx is equal to x minus 5, that's just the integrand. Then we know that, it's an absolute value, so it's positive. When it's positive, if the inside is negative, then it's a negative of that. And that's what this is saying right here. But if you want to write that in terms of drawing, it's just x minus 5 is going to be, it's going to be x minus 5 when x is greater than or equal to 5, or, negative x minus 5 when x is less than or equal to 5. So we can just graph that, and this is what we get. You basically get this like 10 kind of thing. Let me just do that. But the thing is, though, it's like these are all straight lines. This right here is a straight line. This right here is a straight line. This right here is a straight line. This was actually orthogonal, or perpendicular. So that actually forms a right triangle with sides of 5, 5. So the area of that triangle will just be 5 times 5. Base times height. So, we'd note that we could do the Riemann sums, we could do that, but sometimes you could use geometrical arguments. So in this case, it's just two triangles whose areas are just, 1/2 times base times height, which is, 1/2 times 5 times 5. So really, instead of doing the Riemann sums, instead of doing the limits, we could just, actually just calculate it ourselves using what we know about triangles. So the definite integral here will just be the sum of the area of the two triangles. It'd be the left one is going to be 1/2 times 5 times 5 plus 1/2 5 times 5. Add them up, you just get 25. So that's pretty awesome. This is just like a trick we can do. Sometimes, it may not be easy if it's if you have curved lines basically make it you can't really do that. But if you have straight lines on your graph, then, if the function's kind of straight in some way, then you can definitely try to do that. One of the things we also have to do is, define, one of the things we've done is define the integral assuming, A is less than B. That when we integrate that this number right here is smaller than this number. And we didn't really define the integral to be something specific, but we can make, the left endpoint to be the right endpoint. We can make A be greater than B. So what does that really mean? It means that, we reverse AB in terms of delta x. It's basically just when you integrate, you go from the left-hand side to the right-hand side. And we can go from the right-hand side to the left-hand side. But the problem is that, if we start from the right to the left, then if we go from this was 1, this would be 0. So in order for us to go from here to there, we'd have to subtract 1. And that's going to be our delta x. So typically our delta x is going to go from b minus a divided by n to a minus b divided by n. Because again, that's what it means to kind of reverse them. But, a minus b divided by n is just equal to the negative of b minus a divided by n. So what that tells us is that the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. So basically, the integrals are the same, but one's the negative of each other. So if instead of going from left to right, you can go from right to left. But the fact that you're now going from right to left has some consequences to it, and now you become negative. And one last thing is like, if you do the integral, if you do a is equal to b, if you just, try to integrate over one area, then your delta x would just be, a minus a divided by n. But that's just 0 divided by n, so that's just 0. So your area, not the area, but the definite integral, like the integral from a to a of f of x dx, that'd just be 0. Because, again, like the whole argument of it is the Riemann sums, where each thing has being multiplied by a delta x, but if your delta x is 0, then you have no area. And then, we have some properties of like, the sums, so we also have properties of integrals because of that. So like if you do the integral from a to b of c times dx, that'll just be c times b minus a. Think about it as just like a rectangle with like, length of b minus a with a height of c. Area of that rectangle is just c times b minus a, where c is again a constant. We also have like, these other kind of nice properties that kind of go hand in hand with like limits and sums. Because basically those properties with limits and sums do correspond to integrals, because that's how integrals are defined. So the integral of the sum of two functions is going to be like the integral of f of x plus g of x is equal to the sum of the integrals, so the integral of f plus g of x. So basically this tells us that the integral breaks over the sums. Likewise, it also breaks up over differences. The fact is that c is also, if you do c times f of x, remember that the definite integral is going to be, a limit and a sum. So the sum, we said we could pull out that number c, and for the limit, we could also pull out the number c. So we could pull out the c from the definite integral as well. And you can verify this on your own. You could just, use the definition, plug in c times f of x, and then it would still work exactly the same. And now this one is the one that's a bit different. So when we integrate, we go from like a to b. And then, that's going to be the first integral. And then the second integral is going to go from b to c. So b to c. So, like, we could also just, we would expect that would be the same as just the integral from a to c. So that's kind of the case, is, it doesn't really matter, like, if you break up, if you can integrate over the pieces, it doesn't, like, over the pieces separately, and then just add them up. Like, that's totally okay. And this is actually really important, and that's kind of the more useful things we see. Well, one of the, that's going to be the basis of our next example. The next one we could do is, the integral from a to b. Well, yeah. So just kind of keep this in mind. This will be for the example we're going to do real quick. The next three are kind of complicated. They're running out of time because I do have to go somewhere in a bit. But let's just say, f of x is greater than or equal to 0 for x between a and b. And we have the integral from like a to b of f of x dx and be greater than or equal to 0. So basically, like, okay, I'm just going to say that. So basically, if f is positive, if f of x is greater than or equal to 0, the thing you're integrating is going to be greater than or equal to 0, and you'd expect your area under the curve to do this, to also be the same. Likewise, if you have f of x greater than or equal to g of x, so for some area, then the integral over that area of f should also be greater than the integral of g of x. And then, the last one is that if you have m, which should be less than or equal to f of x greater than or equal to m, so f of x is between two numbers, say like its minimum and its maximum, per se, on some interval, then we have these chain of inequalities. So what we really have is the integral from a to b of m times dx, well, m dx, less than or equal to the integral of a to b of f of x dx, less than or equal to the integral of ab m dx. So this one right here is basically just this, but instead of like, with m and f. And then likewise, this one right here is the same thing as this, but, now the things are swapped. And so that's how we get these inequalities right there. We have that the function is going to be between two things. And then lastly, these integrals right here, the integral from a to b of m dx. We already said what those are whenever those are constants. So instead of c, it would be equal to m or capital M. And that's how we get m times b minus a times little m times b minus a. And, this kind of makes sense geometrically too. If we just have like a small like function right here, let's say this is f of x. Say this is like little m right here. So then obviously if we just do the area under m right here, then obviously, that's going to be less than the area of f of x, because we're still missing, this chunk right here. But let's just say this is capital M, and we do the area of this. So this is going to be including this much as well. So the area of capital M is going to be this much. The area of f will be just this much, so it's going to be less. And that's how we get these chain of inequalities. It might seem weird, but honestly, all those symbols, all that math, is just a way to talk about this situation, but being specific. All right. So sorry to blow through kind of fast, but their last example is kind of easy. So the thing is, area, is a number. So what can we do with numbers? We could divide by them, we could multiply by them, we can add or subtract areas, we can we could do a number raised to that number, we could do 5 to the number or whatever. But the thing is, areas and numbers, we could treat them as numbers. So we can, move things over to the other side, and they behave very nicely. So if the area, or the integral of 1 to 5 of f of x dx is equal to 12. So this is going to go from 1 to 5, and the integral of 4 to 5 of f of x dx is equal to 7, so 4 to 5. And we want to find the integral from 1 to 4 of f of x dx, again 1 to 4. So remember that, here we would integrate from 1 to 5, and here also we know from 4 to 5. So we know this piece, we said this is, 12, and we know this piece right here, and we said that's equal to 7, and that should tell us what this piece is. Because we'd expect, this plus this is going to equal to 12. So that's basically the idea. So you get this expression right here, the integral from 1 to 5 f of x dx is equal to the sum from 1 to 5 from 1 to 4, plus 4 to 5, integrating over those areas. And then what we could do is just take this piece, move it over, because again it's just a number, we can treat it like that, and what we get is just this piece by itself. So the integral from 1 to 4 of f of x dx is equal to the integral of the whole piece minus the smaller piece, the other piece. So we get 12 minus 7, so you just get 5. So this wasn't too bad or anything, but it's still it's sorry to blow through, but this stuff isn't too bad. If you're struggling with understanding it, try to understand the geometry behind it. Try to look it up, understand, try to draw some pictures. There's a lot of stuff, it looks complicated, but really it's just geometry. If you can understand the geometry behind these things, if you could try to match up the pictures, what we want to be true, then it should really help a lot. But thank you guys for watching. Comment and subscribe. Peace out.